Hello, pre-calculus students. As we discussed in class the other day, it seemed a lot of students like just to have these videos just to kind of copy the notes and get a brief introduction to the material. And then when we get back into our Zoom classes, um, I'll give you more of my, instruction you can add to these, lecture notes. So let's go ahead and do that. What you see on the screen right now is, I shouldn't have that over here. I should have that. No, I got to keep it there. Is some information about parent graphs. And if we want to stretch a graph vertically, make it taller, we multiply the entire function by a, as long as a is not 0 or 1. If we want to reflect it over the x-axis, well, that a value's got to be negative, because you can see then that your positive y values will become negative y values, and that'll flip you over the x-axis. And then to translate, if you replace x with x minus h, you go h units to the right, and y with y minus k, you go k units up. You should already know how to graph these functions, what those look like. So if I give you the equation of a line, you should be able to graph that bad boy with a quickness. Same with parabolas, cubics, and square roots. If you don't know that, then that's something that we need to review. So now, again, if we multiply our function by a constant a, that stretches it vertically. So think of what y equals x squared looks like versus y equals 3x squared, what that looks like. So what we're going to do now is we're going to graph in Desmos all of those functions that are in green at the bottom of this slide. So please write those down, those functions down, give yourself some room to graph each one. Alrighty. So now you should see my Desmos screen, and I have graphed the function y equals x squared. Now, you'll notice that we're going to multiply that entire x squared function by 3, which should stretch it vertically, make every y value 3 times as tall. And sure enough, that's what it did. So this point 1, 1 became the point 1, 3. This point 2, 4 became It'd be 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 3 times as high. Now, what happens if instead of positive 3, we multiply by negative 3? So here's our 3x squared. Notice that negative 3 just reflects it over the x-axis. Essentially, you could think of it if we move that negative over here, you'd have negative y equals 3x squared. We'd have replaced y with negative y, which flips things over the x-axis. Now here's a square root function. X can be 0, but it can't be negative, so that graph starts there at 0, 0. Now what happens when we multiply the entire function by 1/2? We're stretching it, but only by a factor of 1/2. We're actually squishing it, because we're multiplying all the y values by only 1/2. So when I graph that, you can see all the y values are only half as tall. Now, what happens to a graph when we replace x with negative x? Think that to yourself. What happens to that graph? So here we have y equals the square root of x. Here we have square root of negative x. It reflects around the y-axis. Because what was the y value for 5 is here, the y value for -5, it's the same y value, it's just the opposite x. This next function is my favorite function to graph. If you ever have a graphing program or a graphing calculator or something, try this function, y equals x to the 2/3. Because I've seen a lot of graphing programs and calculators that can't graph this correctly. So this is like my test. You'll notice that it's you square a number, so whether it's positive or negative, it's going to be positive, except for 0. And then we're going to take the cube root of it. So this function should always be either positive or 0. Oops, shut that off. And there's y equals x to the 2/3 power, my little seagull coming at you. I've seen ones where it only graphs this part. I've seen ones where it takes this part here and flips it down here, so you have what looks kind of like an x cubed function or a cube root function, all sorts of stuff. But this is y equals x to the 2/3. Now, we should also have learned that if you take a function and replace x with a times x, you're going through the x's faster, so it's going to compress your graph horizontally. Think of it this way. If you're driving to Reno, if you drive twice as fast, it's only going to take you half as long. So we do y equals x squared, we get this graph. 2x squared should squish it horizontally, and it does. Of course, you might say, well, can you tell the difference if it's stretched vertically or squished horizontally? Well, especially in a parabola like that, you can't, because this green graph here is actually still y equals 4x squared, 2 squared times x squared. But you can accomplish it by stretching it vertically or squishing it horizontally. And yeah, I'm using not very mathematical terms. I get that. So you should have graphed all of those. Let's get back to some more of these slides for you to record. Now, this is a piecewise function. Boy, a lot of people don't like this. We split it up, we split a function up into pieces because there's no real way that we know of to write a function like this, a kind of straight line here and a parabola over here. So f of x, just think y equals -x. That's this line. And it would keep going down here, but it says y is only equal to -x from -infinity to 0. So, -infinity is out here. So this line comes down like this. And you can get as close to you want as 0, but you don't touch because it says doesn't say equal to here. And then at 0, y is no longer equal to -x, it's equal to x squared. Hey, turns out it's the same value. So this graph is what's called continuous. You could graph it without having to lift your pencil off the paper. So this is y equals x squared. So this area over here is the domain. We'll talk about the range in class. Here's a piecewise function that is not continuous. Y equals -x, but from -infinity to 0. But starting at 0, it's x squared plus 1, so it bumps up here. So you have to draw the open circle saying you can get as close to this point as you want. It's kind of like a school dance, these asymptotes. I mean, these points where it's getting closer like this. You can get as close to you as you want at that point, but you can't touch. Then you pop up here. So my question is this a function? I want somebody to ask me that in class if you're not sure of the answer. Here is another piecewise function that is discontinuous. You see y equals negative x down here, and this time it touches 0. And then you can tell the domain of this function, what's underneath the radical, has to be 0 or greater, which means the domain has to be 1 or greater. So the graph doesn't even exist in here. This interval from 0 to 1 is not in the domain. Now you might recognize this function without looking at this piecewise part. What function is that? If you're not sure, ask in class. So this is y equals negative x. This is y equals x. And notice I put the equal sign down here, but since they equal the same value at 0, both negative x and x both equal 0 at 0, so this graph is continuous, I could just as easily have put the inequality on the first one. What you don't want to do is you don't want to put the, the equality on both of them. On one of them. You don't want to put the equality on both of them. That can cause problems. So it didn't matter in this case where I put the equality. They're the same point, but sometimes you do have to watch that. There are special types of piecewise function. This is called, or these two are called step functions. For instance, let's say that this is hours that the garage works on your car, and this is how many dollars they charge. You can see they charge $100 per hour for any hour or fraction thereof. So that's an open circle here, because if they don't work on your car at all, they don't charge you anything. So that's 0, 0 is the point there. The moment you go, oop, the moment they've worked on your car 1 second, boom, they're charging you $100. So you can see it's an open circle up here, out here to $1 is the closed circle. And then at 1 hour and 1 second, oh, they're charging you for the full hour, and then the fraction of that second hour, you're already up to $200. So that's how, there's a graph called a step function. You can see this particular one is open on the left, closed on the right for each step. This one is down here. This is like for a postage stamp from 0 up to a certain number of ounces. You pay, I don't even know what a stamp costs anymore. Heck, they even lowered the price, I think, this year. So is it 54 cents to mail a letter? I don't know. Mine are forever stamps, so it doesn't even have a number on them. And then anyway, once you get to this number of ounces, you're still paying that 54 cents or whatever. The moment you have that extra little fraction of an ounce, they bump you up to the next cost, up until this number of ounces, and then bump you up here. So up here, every step was the same width. They didn't have to be. This might be from 0 to 5 ounces, from 5 to 8, from 8 to 15 ounces. I don't know what the post office does, but you get the idea. In a generic one, the steps don't even have to be equal width. Here, they did have to be equal width. Notice it's a step function, so that should give you an idea. Does this pass the vertical line test? The answer is yes. If you're not sure why, ask about it in class. And then there's the greatest integer function. And the way we write the greatest integer function is we put 2 brackets to the left and 2 brackets to the right. And what that greatest integer function means is, the way you read this is y equals the greatest integer less than or equal to x. So let's take a look. Let's pick some values. I just went 0, 0.1, 0.2, 0.3 all the way to 1. 1.1, 1.2, 1.3 all the way to 2. That should give us an idea of what this graph's going to look like. So the greatest integer less than or equal to 0 is 0. 0 is an integer. 0.1 is not an integer. That's a rational number. The greatest integer, so the largest integer less than or equal to 0.1 is 0. Until you get to 1. And then the greatest integer less than or equal to 1 is 1. So you can see how I generate these numbers here. You should see how these numbers give us this graph. We'll talk about it more in class. And if somebody reminds me, if you remind me, I'll give you an extra credit assignment related to the greatest integer function. So that's all I have for you in this video. Have a great day.